My name is Christopher Lusick. This is my video lab report for Lab 2, Motion of a Falling Object. For this lab, I developed the following problem statement. How does the force of gravity and the drag force affect the motion of a falling object? The answer to this question is important because it will help us understand the different forces that act on objects that are falling due to gravity. To complete this lab, I use Newton's second law, the momentum principle, tracker, and GlowScript. First, I'll explain Newton's second law in relation to this lab. The momentum principle states that the net force is equal to the derivative of momentum with respect to time. This means that when there is a change in momentum, there is a non-zero net force acting on the system. F net can also be thought of as the sum of the forces. The sum of the forces acting on a falling object is mainly the force of gravity and the drag force, which act in opposite directions. In addition, as the object's velocity increases, the drag force increases in the opposite direction. This is displayed in the free body diagram to the right, with Fg acting downwards, F-drag acting upwards, while velocity is downwards. My procedures for this lab were to drop a ping pong ball and record it on camera. Using the ruler in the background of the video, I was able to track the distance the ball fell over time in Tracker. I then used GlowScript to make two computer models of this situation. One model was with only the force of gravity, and another model included the force of gravity and the drag force. Here's the original video of the ping ball falling. Using Tracker, I tracked the position of the ball falling over time as shown here. This produced a position versus time graph with data points shown on the side. With the ball starting at rest, I could see how the ball accelerated as it fell. I then made the two computer models of this falling ball. I input the known radius and mass of the standard ping pong ball, its initial position at the origin, and its initial velocity of 0 because it starts at rest. I then input the timed run for 0.5 seconds, as this is how long the ball fell in my video. In this first model with no drag force, F net is equal to the force of gravity, mg. When I hit run, a model of the situation is shown with position versus time graph and data points shown here. I then repeated this code while changing F net to include the force of gravity and the drag force. The magnitude of the drag force is equal to the constant v times the velocity squared, but the force acts in the opposite direction of the motion. This made F net equal to Fg minus F drag. When I hit run, the model is shown with a new position versus time graph and data points for this new situation, including the drag force. To further clarify, Model 1 includes just the force of gravity where F net equals Fg. This is shown in the free body diagram where Fg is the only force acting on the ball. Model 2 includes both drag force and force of gravity where F net equals Fg minus F drag. This is shown in the free body diagram here. F drag increases with increasing velocity, and b is constant that depends on properties of the ping pong ball. I then graphed these different data points. The blue observed position line was obtained from the data points in my Tracker video. The red line is the model with no drag force where F net equals Fg. The orange line is the model that includes drag force, which is much more accurate as it ends in the same position at the same time as the observed ball. It is more accurate because it includes the drag force, which is present in the observed data. Improvements I can make to this lab include getting a higher quality camera and using a device to drop the ball. Less blur in the camera would allow me to accurately track its position instead of clicking the middle of the blur, as shown in the picture. Using a device to drop the ball would ensure that it actually starts at rest, as I may have accidentally given the ball a small initial velocity. This could make the model with drag an accurate representation of the true events in my observed video. I then answer the question, what does it mean? The model that includes the drag force predicts a terminal velocity when F net equals 0. As the velocity increases and F drag increases, F drag will eventually be equal in magnitude to Fg. When this happens, F net equals 0, so velocity will be constant at this constant velocity, as shown in the diagram and proven by the momentum principle. I then answered, what if the object was initially thrown downward? The answer is that the terminal velocity does not change based on initial velocity. The terminal velocity depends on the properties of the object and the properties of the medium it is moving through. Dropped or thrown objects will increase in speed to a terminal velocity. If the object is thrown faster than its terminal velocity, it will slow down to its terminal speed after being released. This is because terminal velocity happens with F net equals 0, which does not depend on the initial velocity. In conclusion, the force of gravity and the drag force act on falling objects in opposite directions. Drag force increases with increasing speed. Also, when the drag force is equal in magnitude to the force of gravity, the object reaches a terminal velocity as F net equals 0, and the velocity becomes constant. This concludes my video lab report. Thank you.